Let's do the analysis. So the analysis of our boost converter. So as we mentioned, we have our E, we have our RL. Here we add our switch, diode, and here we have our V source. So this circuit has to be solved twice. One during on condition and one during off condition. So during on condition, this diode will be open circuit and the switch here will be short circuit. And during off condition, the transistor will be open circuit and the diode will be short circuit. So in this case here, if we assume that this is the direction, and this is very important, okay? If this is the direction for I out, so I out here will be charging, okay? So the current here will be charging. This is T on, this is I versus time, and this is I1 of T. So I1 will charge from a value I minimum and it will reach a value I max as we did for boost converter or first quadrant. To write the equation for I1 of T, it's I initial exponential minus T over tau plus I final 1 minus E minus T over tau, and this is a generic transient equation. So the initial current I initial is the minimum value I min, or we named it as I1 capital, plus the final. When the inductance is short circuit, the final current is simply E over R. So the final value is E over R 1 minus E minus T over tau, and this is the equation for I1 of T. And if we find I1 of T equal T on, this should equal to I max equal to I min E minus T over tau plus E over R 1 minus E minus T divided by tau. And this is an equation, and in this equation there is two unknowns, I max and I min. And during the discharging time, which starts as time T on and goes up to T, and we start from I max and we go to I min, and this equation is I2 of T. So I2 of T equal to, the initial value is I max, and don't forget the shifting of axes, and the final value when the inductance is short circuit, the final will be E minus V divided by R. So the final is E minus V divided by R, 1 minus E minus T on divided by tau. And I2 when T equal to T capital is I min. So at time T, the value is I minimum, which equal to I max E minus T on divided by tau plus E minus V divided by R1 minus E minus T on divided by tau. And this is the second equation. And this equation also is an equation in I minimum and I maximum. So we can solve this equation to get we can solve these two equations so we can get these expressions. So this is I1 or I minimum, and this is I2 or I maximum. And as you can see that I out average according to KVL, so don't forget the direction of I out as we mentioned here. So I out average will be E minus VS K, minus VS 1 minus K divided by R. and this will be our average equation. So it's E minus V average over R, and V average is 1 minus K multiplied by Vs as we did the proof before. Don't forget the definitions for K is the duty cycle T on over T, Z is T over tau or TR over L, tau is L over R, and T is 1 over frequency. So this is the equation for I minimum, and this is the equation for I maximum. So I minimum greater than or equal 0, this is the condition for being continuous. So this is a continuity check. So the continuity check that the minimum is greater than or equal 0. You may find different equations in the textbook, so please be cautious in this part. So some textbook assumes the current I out in the opposite direction, which will change your average equation here, and it will change the equation for V and E. So it will be reversed. So pay attention to this equation and don't just use any equations online. So these equations will be provided to you during the final exam. So these are the equations we need for the boost converter, is the average equation V average, the maximum and minimum currents, and I average. Now we can solve an example from the problem set. So let's solve this example on DC to DC converter boost converters from the problem set. So we have a DC to DC converter. It is in second quadrant operation, and the battery is 200 volt. The armature resistance is 1 ohm, and the inductance is 1 millihenry. So you have an electric vehicle going downhill, and if you are going downhill, you have overspeed and you can do regenerative braking. If you are going flat on a flat surface, you are doing forward motoring. So here you can do the first quadrant, and here you can do the second quadrant to brake the machine. And as we will learn later on, that we can use first and second together, which is called two quadrant. Okay, now we are on the second quadrant only. So you are going downhill at constant speed. The back EMF is 150, and the braking current, okay, highlight this, it's a braking current. Braking means it's going in backward. So the battery is 200, the back EMF is 150, the inductance is 1 millihenry, resistance is 1 ohm. And we need to calculate the duty cycle if the current is continuous output current. Okay, sorry, we need to find the duty cycle. So how we can find the duty cycle for this example? So we start by V average equal to 1 minus K multiplied by V source, and we have I out average equal to, if you define I average in this direction, so it's going from E to V, so it's E minus V average divided by R. If we define I average to be going in this direction, so I average should be V average minus E over R. So pay attention how you define your current. So the current going from the source to E, so it's V average minus E. If the current going from E to V source, it is E minus V average. So this current is 10 amperes, and this current should be negative 10 amperes. So I out average equal to 150 minus 1 minus K, Vs is 200 divided by R, and the R is given as 1 ohm. and this I out is 10 amperes. So the only unknown in this equation is K, so K equal to 0.3 or K equal to 30%. So the duty cycle is 30%. So if we sketch our V out, so here is 0.3 T, here is T, and during this time the voltage is 0, and during this time the voltage is V source, and V source here is 150 volt. So we can sketch our V out. So calculate the duty cycle. We calculated the duty cycle. What is the minimum frequency to be continuous? So here we have a continuous current and we need to find the minimum frequency. So don't forget that the continuity equation is I1 equation. It's hard to So this equation will be in the formula sheet of the exam that I sent you. So this is the equation for I1. So for continuity, what we should do, so this equation has to be greater than or equal 0. And for this equation to be greater than or equal 0, we can make this equal or greater than, and this will be the condition. And R can cancel R, so the equation is E is greater than or equal V source 1 negative E minus 1 minus KZ divided by 1 minus E minus Z. Now we have K as 0.3, and the only unknown in this equation is Z. E is 150, V source is 200, correct? So we have to correct this to 200. So 150 equal means this is the minimum value. So equal to Vs is 200 multiplied by 1 minus E power negative Z divided by 0.3 Z divided by 1 minus E power negative Z. And you can solve this equation using your calculator, your solve function. And to be easier and to be able to solve it directly, what you can do, you can assume that E power negative Z is X. So the equation is 150 equal to 200, 1 minus X power negative 0.3, power positive 0.3 divided by 1 minus X. And you can write this equation and then you do shift and solve, and you have to put an initial value for X, say 0.1, and you press equal, it will give you X. Once you have X, you can get Z, and once you have X, you can get the value for Z, and the value for Z is function of R and L and frequency. So X will be 0.66, which is E power negative Z. So Z equal to negative ln 0.66 equals to Z is TR over L. or R divided by LF. R is 1 ohm and L is 1 millihenry. So the only unknown will be the frequency, and this frequency is the maximum frequency, is 2.02 kHz. So please make sure that you got this number when you are solving this equation. So the maximum frequency to be continuous is 2.02 kHz. Now at this speed, which is at E150, so speed means E from motors, determine the minimum duty cycle for continuous inductance current if the switching frequency is 1 kHz, and what will be the average breaking current at this critical duty cycle. So again, at this speed at E150, determine the minimum duty cycle for continuous current if the frequency is 1 kHz. So we will go back to this equation here. So E is 150 equal Vs is 200 multiplied by 1 negative E power negative 1 minus Kz divided by 1 minus E minus power minus Z. Z is R divided by LF. R is 1 ohm, L is 1 millihenry, and the frequency is given 1 kHz. So this Z is 1. So the equation becomes 150 equal to 200 multiplied by 1 negative E power negative 1 minus K divided by 1 minus E power negative 1. So the only unknown in this equation is K minimum, the minimum duty to be continuous. So we can find K to be 0.357. So this is the minimum duty cycle to be continuous. Why? So the duty cycle is the on time divided by the whole time, and during the on time you are charging, and during the off time you are discharging. To be continuous, you need to increase the charging time and decrease the discharging time, so the current will not go to zero faster. And to increase the charging time and decrease the discharging time, K has to go up to be continuous. That's why this K is K minimum. This is the minimum K at which the equation is just equal. Now if you increase K more, this equation will not be equal and it will be greater than, or your current will not go to zero, it will go to a positive value. That's why we call this K minimum. So the minimum K for continuous current is found here. Now if the switching, what is the average breaking current at this critical duty cycle? So to get the average current, I out average is E minus 1 minus KV source divided by R. E is 150, K is 0.357, V source is 200, the resistance is 1. So we can find the average current. So we can find easily what is the average breaking current, which is 21.4 ampere. The next part here is if the frequency is 5 kHz at the same speed, which means, so in the exam I don't have to say that E is 150. Same speed means same E. What are the critical duty cycle and the corresponding DC current? So that just he changes the frequency to 5 kHz. So what we will do, we will go to the same equation. So just we are repeating this equation with different frequency. So here just the frequency here is 5. So this Z is 0.2. So here it's negative 0.2. Negative 0.21 minus K divided by negative 1.2. So again, the only unknown here is K. And you can see that K, or the minimum duty cycle, is not a constant value. It depends on the frequency and the other conditions. So the only unknown in this equation will be K. So K in this equation will be 0.267. Once we got K, we can say that I out average equal to E minus 1 minus K V source divided by R. E is 150, V source is 200, and we have K, so we can calculate I out average, which means you can be asked to calculate minimum duty cycle to be continuous, maximum E or maximum speed before being discontinuous, minimum frequency to be continuous, maximum frequency before being discontinuous, etc. So you can be asked for any variable. It's one equation. For I minimum, it's one equation, as you can see. So in this equation, I have to give you all the variables except one. And the variables you have, so Z is R divided by LF. So the variables you have here is frequency, inductance, duty cycle, and E. So I have to give you all the variables except one. So I can ask for the duty cycle, or the maximum speed, or the inductance, the minimum inductance, or minimum frequency. Okay, so this is the boost converter. So I will stop the lecture here and we will continue in the second part.